like e to the lambda t, t e to the lambda t, etc., up to t to the power r minus 1 lambda t, e to the lambda t, where r is the multiplicity of this eigenvalue. Okay. So in all cases we can analyze it in principle and write down the solution. Now the moment you have a thing like that, the moment you have a structure like some coefficients e to the lambda I t, I equal to 1 to n, then the asymptotic behavior of the solution will depend on the asymptotic behavior of these exponentials, and that in turn will depend on whether the real parts of these eigenvalues are positive, negative, or 0. And then it follows that the space itself, the linear vector space, is now broken up into 3 subspaces which are invariant under the flow. And those invariant subspaces are the following. So you have the span of all lambda I such that real lambda I is greater than 0. And the span of the subspace lambda I, real lambda I, less than 0. And finally the span of all those eigenvectors whose eigenvalues have the real part equal to 0. The asymptotic behaviors of these are completely different because these guys would diverge away from the fixed point or the critical point. These would flow asymptotically into the critical point, and these would be indifferent, neither flowing in or out. In general, if for instance something is pure imaginary, then it will just have cosines and sines and they will oscillate about it. Now this thing here, this span of this space, it's a subspace, it's a linear vector space. Remember that we have linearized the system. This is not the full nonlinear flow. The full nonlinear flow is here, but this, in the vicinity of the critical point, is a linearized flow. So that's very important. It's linearized. Yes. And this linearized flow, this thing here is a differential equation with constant coefficients. The eigenvectors span the tangent space at that point, and that's a Euclidean space like all tangent spaces. And that Euclidean space is now being broken up into 3 subspaces which together constitute the full space. And the span of all these eigenvectors corresponding to such eigenvalues is called the unstable manifold.
So what is tangent?
I'll explain this with examples immediately. But it's called the unstable manifold, and it's denoted by EU because it's a Euclidean space. This is a linear equation that's completely Euclidean. Now, okay, I don't want to. I said I'd be very cavalier in my statement in my mathematics. So, what I mean by what do we mean by a manifold? In general in mathematics, a very crude definition is that it's the generalization of the idea of a smooth curve or a smooth surface, right? As opposed to a tangent space, which would be a straight line or Euclidean plane and things like that. So this thing here is the so-called unstable manifold. This is called a stable manifold. E stable, and this thing is called a center manifold. I'll give some examples that will make it clear to you. And the statement is the following, and this is a very deep theory. It says that the actual nonlinear flow is some very complicated thing. So here is a fixed point, and in the vicinity of it you've got some nonlinear flow, maybe like this. These are the flow lines or something. But if you go very close to it and look at a linear problem, then this flow would get essentially sort of distorted into something like this. And we will see this explicitly. No curves, just straight lines. These are the eigenvectors or eigendirections, if you like, of which these eigenvectors specify. And the statement is, if you do not have any eigenvalue at a critical point, which has real part equal to 0, but only positive or negative real parts, then this linearization procedure is a reliable and accurate and unique way of prescribing the flow arbitrarily close to the fixed point or the critical point. In other words, the linearization is reliable it gives results, correct results, as long as there is no center manifold. But the moment some of the eigenvalues, one or more of the eigenvalues, has a zero real part, then this is no longer guaranteed at all. And we'll see examples that then the matter becomes much more complicated, and you have to take the course to more sophisticated methods. And there's a whole slew of results going under the name of center manifold theory. There's books on it. And it tells you what to do in cases when you have problems with the center manifold. And I'm going to give some specific examples, where you'll see simple examples, how unreliable it can become once you have a center manifold. But this is the general philosophy. As long as you have just this and this, as long as there are no zero parts to the real parts of any eigenvalue, there's no zeros, then the critical point is said to be hyperbolic, and you have things either flowing away from it or into it, depending on whether the real lambda is positive or negative. And that is called the Hartmann-Grobman theorem. And I will write that theorem down a little later. But let's look at some examples and see in what sense this is tangential and how and what happens when you have real nonlinear flows. Yeah.
Just to make confused, we are looking near the critical point.
Right.
And if there's a long time limit, we are going to go very far away from it.
Yeah. Oh, so it's no longer, once it leaves the neighborhood, yeah, I get your point. Once it leaves the neighborhood, there is no sanctity to this. Then the flow can go somewhere else altogether. This exponential form is no longer true. But the fact is, if you are very close to the critical point, and you have an exponential which diverges, then there's no doubt at all that you go away from this point. That's all that's being looked at. So here's the critical point, and if you start here, you definitely go out. That's all that is, and it's exponentially so.
It just means it's going to go out of the...
It just means it's going to go out. I have not yet started defining what's meant by stable, asymptotically stable, unstable, and so on. I will do so. Yeah.
Are these subspaces of tangent space or phase space?
The idea is that the real manifolds, the stable, unstable, and center manifolds, there exist stable, unstable, and center manifolds, which are called WU, WS, WC. And these Euclidean spaces are tangent spaces to those manifolds at the critical point.
Subspaces of our phase space, phase manifold.
Yes, of the full n-dimensional phase space. Yeah, in the vicinity of this critical point. And the point is, the statement in a nutshell is that this linearization procedure tells you how to find these two fellows, as well as this. There exist true unstable, stable, and center manifolds in the vicinity of that critical point, to which these are tangent. But the problem is, these are unique tangents to these subspaces. This is not a unique tangent. So the uniqueness is lost. And I will again give a very simple example where you'll see this explicitly.
So what are these WK, WS, and...
Yeah, they are the, let me do this with examples, and we will see immediately what. The best thing to do so this abstract thing is to actually write down simple examples of this whole thing. But one thing I would like to impress right in the beginning is that, in general, since these eigenvalues are independent of similarity transformations, you can always make a linear transformation on your coordinates in any number of dimensions, and under that distortion, the character of the state of the fixed point or the critical point will not change. In other words, if real lambda is greater than 0 in the original coordinates, I make twists, I rotate, I change, I distort, etc. It's not going to change. The flow shape will change, but otherwise it's not going to change. And now let's look at very simple examples of this, and we'll come back to the formal a little later. Since I'd like to draw pictures, let's look at it in a plane, 2D systems. And let's look at x dot is f of x comma y, and y dot is some g of x. Just a plane. And let's say that we have a critical point or a solution of the simultaneous equations f equal to 0, g equal to 0, and let's shift the origin to that critical point without loss of generality. So, critical point at 0, 0. then the linearized equation in that neighborhood is very easy to write down. L is equal to delta f over delta x, delta f over delta y, delta g over delta x, and delta g over delta y. Evaluated at x equal to 0, y equal to 0 at the origin. And let's just call this sum A, B, C, D. And we need the eigenvalues of L, and that's easy to write down. It's clear that lambda squared minus A plus B, lambda plus AD minus BC equal to 0. So the two eigenvalues are lambda 1, 2 is minus, is A plus B, so that's equal to the trace plus or minus the square root of trace squared minus 4 times the determinant over 2. T is the trace and delta equal to AD minus BC is the determinant. So as promised, the eigenvalues depend only on the trace and the determinant, both of which are invariant under similarity transformations. We can therefore classify all possible flows near the origin, which is a critical point, by asking what do these flows do? When is the real part greater than 0, less than 0, equal to 0, etc. And that way you can find out which is stable, which is unstable, and so on. So let's do that. Let's take the simplest of cases. And after that, we can change variables and distort it to look at more complicated cases. So let's look at x dot, so 1. X dot equal to x, y dot equal to y. This is simplicity itself. Both the eigenvalues are real, and both of them are positive, because it's a diagonal matrix, unit matrix here. And what does the flow look like? It's completely trivial here, because except at the critical point, in which case there's no flow at all, that's a stationary point. Except for that, wherever you are, x increases linearly with time, exponentially with time, y increases exponentially with time at the same rate. So it's clear that the flow lines look like this. That's what the vector field looks like. Had this been 2y, for example, then the y is going to go like e to the 2t, while x is going to go like e to the t. Therefore, the y is going to increase much faster, and the flow lines would start looking like this. That's a matter of detail. Depends on the actual numerical values here. But this thing here, what would you call this? Would you call this a stable, unstable, or what? It's unstable. And it's unstable in all directions. Whatever direction you choose on the plane, and there are only two independent directions, it's unstable. So in this problem, what's the unstable manifold? It's the whole plane, because what are the eigenvectors? 1, 0 and 0, 1 are the eigenvectors. It's a unit matrix, right? And 1, 0 and 0, 1 actually are the x and y axes, and they span the space completely. So in this problem, the unstable manifold is all there is. Everything is unstable. Wherever you are, you're guaranteed to flow away from this critical point.
So what's the WK here?
Pardon me?
In this problem, what is the WK?
It depends on what your f is. In this particular problem, if this is the actual problem, it's already linear. So that's the full space in any case, the full flow in any case. But had this arisen as a linear approximation to an unstable, to a nonlinear flow like f and g, general f and g, then I'd have to go back and calculate what it is for the exact flow. These flow lines could start curving after some time. And those would be the two stable and unstable. But in this particular problem, the whole plane, so the unstable manifold is the whole
is
plane.
just a tangent space at 0.
At 0. Absolutely. What happens if I had this? What would happen if I had minus x and minus y? All the arrows would be reversed. Everything would flow in asymptotically. As t tends to infinity, everything would flow into the origin. And this means that the whole plane is a stable manifold. What happens if I have this? X dot is x, but y dot is minus y. Now you see, if I start with x equal to 0 as my initial condition, I don't move in x at all. And y decreases exponentially from both sides, so this is a flow line inside here. If I start with y equal to 0 on this line, wherever I start, you flow out like that, you flow out like this. And then by continuity, it's clear that the flow lines will do this. And this thing here is an unstable critical point, and it's a saddle point. The flow looks like hyperbolas locally around it. It's a rectangular hyperbola in this case because this is increasing like the e to the power t. This is decreasing like e to the minus t, so the product is a constant, and you have xy equal to constant. Those are your flow lines, the field lines. But if this went like 2x and that went like minus y, then it would no longer be rectangular hyperbolas. It would look hyperbolic, but it would not be rectangular hyperbolas of this kind. So this thing here is called a saddle point. And we can start classifying. So let's do that. So the first one was lambda 1 to greater than 0. This thing here is called an unstable node. The critical point is called an unstable node. It's like a source. And 2, lambda 1 to less than 0, it's an asymptotically stable node. Asymptotically things are going to go into this. 3, one of them is positive, or vice versa, it doesn't matter. This is a saddle point. And of course it's unstable. But this example already tells you what's the stable manifold and what's the unstable manifold. These tangents, these are the tangent spaces. In this case, the L matrix looks like 1, 0, 0, minus 1. So 1, 0, this column vector is an eigenvector with eigenvalue plus 1, and 0, 1 is an eigenvector with eigenvalue minus 1. So this guy, this line, this direction, this line is the unstable manifold. This line is the stable manifold. So if you're on that line, if the initial condition is on that line, you're guaranteed to flow in asymptotically. But if you're anywhere else, you're going to flow out. If you start here, you're going to definitely go away from the critical point. In the y-coordinate, of course, you're going to get to 0, but then eventually the x will dominate and you'll move off. And together, these two eigenvectors span the space. Is there a center manifold here? There's no center manifold. So this immediately tells you the idea behind these unstable and stable manifolds here. They are really the tangent spaces. What happens? So now let me do one more thing. The actual flow in a more complicated situation would look like x dot is AU AX plus BY, and y dot is CX plus DY. That's like changing coordinates. I can change coordinates to AX plus BY and CX plus DY. And I'm going to assume all along that AD minus BC is not 0. If it is 0, then the mapping is these are not linearly independent equations. Then you have a degenerate critical point. But for the moment, I'm going to say AD minus BC is not 0. Then it's clear that the general flow, if lambda 1 is positive and lambda 2 is negative, or vice versa, would still be a hyperbolic point, but it would no longer have eigenvectors which are normal to each other. Moreover, there could be a distortion in one direction or in the other direction, and there could be oblique axes in general. So this flow is typical of a saddle point, and the general flow near a saddle point will look like this. This is the stable manifold, that's the unstable manifold, and the flow would look like this. And this is a saddle point. So once I've analyzed this simple case, I've actually analyzed all saddle points because they are related to the original orthogonal rectangular hyperbola by a linear transformation. Now what does a linear transformation do? What does from xy, if you go to ax plus by, cx plus dy, what does it do to the plane? What does it actually do to things? If ABCD is orthogonal with determinant 1, then it's just a rotation. If the determinant is not equal to 1, then it's not measure preserving anymore. Areas are not preserved. There could be dilation, there could be rotation, there could be shear in general. And as you know, any 2 by 2 matrix with real elements can be written non-uniquely as a combination of a rotation, a dilation, and a shear. So that's all it does. I start with a unit square. Under a rotation, this square will start looking like this. Under a dilation or a magnification, it will start looking like this. And under a shear, it will start looking like this. And that's what happens. Yeah, any 2 by 2 matrix which belongs to, every 2 by 2 matrix which is not singular belongs to the general linear group in 2 dimensions, GF2, right? And this has 4 parameters. So one of them is a rotation, 2 of them would be dilation or contraction in the 2 directions, and then a shear. Or if you like, 1 magnification or demagnification and 2 shears. So it's not a unique way of transforming. But this is what looks like in general. And ditto for the other cases, the nodes, etc., those stable nodes. So the flow near a typical stable node would look like this. Things flow in, things flow in, things flow in, things flow in, and perhaps they all flow in like this. If the rates are not the same in all directions, they will flow in like this. I've drawn it with orthogonal axes, but it doesn't have to be. This too could be twisted. That would be a typical behavior near an unstable node, near a stable node, asymptotically stable. So having exhausted saddle point, let's look at the next possibility. Well, this exhausts the cases where these roots are real. The next case is where they could become complex, for instance. So let's look at, let me look up an example. X dot equal to, say, x plus y dot equal to minus x plus. Now the L matrix is 1, 1, minus 1, 1, and lambda 1 and 2 are equal to lambda minus 1 whole squared equal to minus 1. So 1 plus or minus I. So now the roots, the solutions look like e to the lambda t, sine omega t, sine t, and e to the t, sine t, e to the t, cos t. Therefore, they would sort of spiral round, and what would it look like near the origin? It would spiral away. Because the real part is positive, so the flow lines would look like that. This would be an unstable. Both x and y would oscillate because of the cosines, with increasing amplitude because of this e to the t. And this therefore corresponds to 4 lambda 1, 2 equal to lambda plus or minus I mu with lambda greater than 0. This is an unstable spiral one. And the spiral could of course be distorted. You can now twist the axes and then it becomes like an elliptic spiral of some crazy kind, but it's still unstable. Had this been minus and minus, then you get a minus 1 and a minus 1. Right? So now the eigenvalues 5 will be lambda 1, 2 equal to its lambda plus 1. So it's a minus 1 plus or minus I in in this case. And the arrows would be reversed. Everything would flow in. So lambda 1, 2 equal to lambda plus or minus I mu, lambda less than 0. This is an asymptotically stable. The arrows go in. In this case, what's the unstable manifold? The complex eigenvalues. It's the whole plane. It's really the whole plane. Because there is no stable direction at all. Wherever you are, you're going to flow out. And ditto here. It's the whole plane. So in 2 dimensions, things become sort of trivial. But when you have n dimensions, when you have a larger number, then things become interesting. For instance, take this same example. Suppose you had a third variable, and it was z dot equal to z. What would then happen? Right now, in the plane, in the xy plane, things are spiraling in towards this critical point, which is asymptotically stable. But if you had a third direction, you had the z direction as well, then your phase space is going to look like this. So here's x, here's y, and here's z. And it's clear that z is exponentially increasing, going out. The critical point is still at the origin. Whereas if you start somewhere, it's going to flow in, but along the z direction, it's going to go out in this fashion. So you have a focus, a spiral point is also called a focus, but this thing has an unstable direction and it's called a saddle focus. Because in one direction it goes out, and that's as good as becoming unstable completely. The moment you have a third direction, then this says z is e to the power t, and therefore is going to increase. So if I start at some finite value of z above the real axis, above the z xy plane, it's going to spiral out. If I start in the other direction, it's going to spiral out the other way. Yeah. Okay, we're coming to that. Yeah. You do not. You don't. You cannot. Because it's changing measure, as you can see. I could have been the other way. That will depend on the actual flow. I must write this in polar coordinates and figure out what it is. Now this thing here, the saddle focus, is a mechanism for chaos in many systems, many dissipative systems. Because then when you switch on true nonlinearity, as opposed to this very simple linear case, what happens is phase space points start like this, go far away, and get re-injected back into the plane randomly, and then they come back again and go out and come back, etc. And you have what's called homoclinic chaos. So this mechanism, this saddle focus, when you perturb it, make it nonlinear, etc., in chaotic systems, is one mechanism by which things which look like they're going to converge to something stable, boom, gets off in another direction, and it goes away. So that's a very, very commonly occurring mechanism for chaos in dissipative systems. We will get back to this. So you can see that there are other possibilities once you have higher dimensions. And what's the last possibility? Pure imaginary eigenvalues. So suppose you had x dot equal to y, y dot equal to minus x. You'll recognize a simple harmonic oscillator here. X dot is p in units of m equal to 1, and p dot is minus x, you put omega equal to 1. So this guy here has eigenvalues lambda 1, 2 equal to plus or minus I. Because the matrix is 0, 1, minus 1, 0. And the eigenvalues are pure imaginary. So the solution is purely oscillating. Just e to the cos t and sin t, because I put omega equal to 1. Things neither come in nor do they go out. So 6, 1, lambda 1, 2, plus 1. What would you call this? So the flow lines in this case are just circles. Or they could be ellipses, or they could be something with the equal close curves. Periodic motion. So you have periodic motion, and the eigenvalues are pure imaginary. You have periodic motion. And incidentally, you now have a center manifold. The whole plane is a center manifold. There is no stable manifold, there is no unstable manifold. Everything is the same. This is the harmonic oscillator, pure imaginary eigenvalues. Because you recall the harmonic oscillator, right? It's a x dot equal to p over n, p dot equal to minus x, and immediately you have eigenvalues which are pure imaginary, plus or minus I on m. So would you call this